Hello and welcome again to my Physics Online video lecture series. Today's video we're going to be talking about air resistance. So this is another of those videos in this series about forces and types of force that we might commonly encounter in classical physics. So this one we're going to be talking about air resistance a little bit, about terminal velocity a little bit, and also about how much air resistance is there for an object, by which I mean, does it, generally speaking, end up being a major source of error in experiments in which you're doing, say, like dropping an object or letting it roll down a ramp or something like that? And the answer to that latter question is very tricky because it kind of depends upon the object and so on. If you have an empty tin can, then air resistance can be pretty substantial. If you have a solid object, like a solid metal ball bearing or a glass marble, something like that, then your results may vary a little bit more. So air resistance is a type of drag force. So drag force, and drag forces in general tend to have force proportional to speed in some way, shape, or form. It may be speed to the first power, maybe speed to the second power, maybe speed to the third power, maybe some other version of speed, some exponential or power or what have you. The point being that typically what a drag force does is that if speed increases, then force also increases. We'll put a little D for drag on this. Now, what is meant by speed here? Well, it's actually the relative speed between the object and the fluid. That is to say, if the object is moving and the wind or the air or what have you is totally stationary relative to your observer, then we could use the object speed. On the other hand, you could have a stationary object and the wind blowing over the object, moving past the object, in which case you would use the speed of the wind. Or you could have a headwind, like a wind blowing directly into your face, for example, and you're running in the opposite direction. So now you'd have to use the difference in those two velocities. So it's a relative velocity thing. By the way, all of these have some application. Wind tunnels, basically you have a stationary object and you blow wind over the object and measure what kind of drag force is applied to the object. If you're actually out racing on a bike or on foot or what have you, or even in a car and there's a wind, then knowing what kind of drag there's going to be against you might matter somewhat. The fluid doesn't have to be air, by the way. It could be basically any fluid. It could be nitrogen gas, it could be helium gas, it could be a liquid for that matter. Now, with that said, the drag force does depend a little bit on what kind of fluid and how fast you're moving. So there's another type of drag force that we'll introduce later called the Stokes law drag, which is usually defined for a spherical object moving slowly or relatively slowly through a liquid, although you can generalize it to a non-spherical object as well. What we're going to focus on today, though, is the drag force that's applied to an object that's moving with some amount of speed through a tenuous medium. And tenuous basically means like low density, like an air. Although a plasma physicist would say that that's not very tenuous, but we'll say air or the like. And as it turns out, for air and the like, your drag force Fd is usually given by half of some coefficient times rho times v squared times cross-section area. Okay, and again, this is assuming a relatively dense or heavy object in a relatively light or low density fluid such as a gas. So this C term right here is what's called the drag coefficient. It's in some sense a measure of how aerodynamic is the object. This A term is what's called the object's cross-section area. So for example, if we have a sphere of radius r, you know that the surface area of that sphere would be 4 pi r squared. The cross-section area would just be pi r squared. In other words, here's my sphere in cross-section. It's circular. Okay, so that's your cross-section area. If you have a cylinder and it's falling flat end first, then you'd use the circular area of that flat end. If you have a person that's skydiving, you'd basically take the cross-section area, like imagine slicing them down the middle mentally, not literally, but mentally slicing them down the middle and then finding the area that their shape would take up. Okay, so that's cross-section area. The drag coefficient typically is measured. Usually you place the object in a wind tunnel and then you vary the speed that you blow the air, the wind, over the object at, and you measure how much force the object is experiencing from that wind blowing past it. And you do that at different speeds, and essentially what you can do is then plot the speed of the wind versus the drag force. So you'd have something like this, and then you can extract C from the fit of these data. If you were doing this, if you as a student that's taking an introductory physics course were to do this, then you've got a nice fancy setup for your physics course for one, but you'd essentially maybe want to plot the data, linearize it, and then the slope should be essentially 1/2 of the density times the cross-section area times the drag coefficient. And you can know the cross-section area from basic geometry, and you can know the density of the wind by essentially assuming like you have air with this density and so on, or maybe you can put a flow rate measure. But the density of gases tends to be temperature dependent, so not constant, but it can be approximately constant for a given room or what have you. So at sea level, at 0 degrees C, so sea level and room temperature, standard temperature and pressure, the density of air is about 1.204 kilogram per cubic meter. If you lower the temperature of the room by 5 degrees but keep the density, keep the pressure the same, then the density will now be 1.225 kilograms per cubic meter. So there is a little bit of difference. This is on the order of 2-ish% difference between these two. So you have to be careful with that. Nevertheless, we might ask how much drag force there is on an object which is falling at sort of like normal dropped speeds inside of a room. Going back to the drag coefficient, I should note that there are some sort of like known values that you can pull out of textbooks or tables of values. So this comes out of the OpenStax textbook. These are the drag coefficient C for a variety of objects. So for a sphere, it's 0.45, and there's no units to that. Most of the other objects tend to be things like airfoils or vehicles, because who is it that spends a lot of money building wind tunnels to test things? Well, basically automobile manufacturers and aerospace companies. Maybe some bicycle manufacturers for like racing bikes and the like as well. So quick example, we have a steel ball bearing of radius 1 centimeter, and it's falling with a speed of 10 meters per second through air at standard temperature and pressure, that is 20 degrees C and 1 atmosphere pressure. And we want to know what the air resistance force's magnitude is, as well as the force from gravity. Alright, the air resistance force, we can use FD as 1/2 C rho V squared. Okay, so that is 1/2, left off the area, 1/2 times C, which for a sphere is 0.45, times rho, which is 1.204 kilograms per meter cubed. That's from this previous slide. Times the speed squared, so that's 10 meters per second squared, times the area, which again is a cross-section area, pi times r squared. So that's pi times 0.01 meter squared. Okay, that a total drag force from air, total air resistance of about 0.0085, let's round it to there, newtons. Now the same thing for gravity. To get gravity, we use Fg is mg, so that would be density of object times volume of object times g. And so we would have 7,850 kilograms per meter cubed for the density. For the volume, we have 4/3 pi times r cubed, so that's in meters. And then for g, we have 9.8 newtons per kilogram. So plugging that into the calculator, we get a total force of gravity of about 0.322 newtons, or 0.32 newtons. So if we divide that by 0.0085, we get a factor of 37. Or put differently, this is about 2.6% of Fg. So that's about how much error that can contribute to such an experiment. One more concept that is kind of necessary when talking about drag forces is the terminal speed. So when you have an object which is falling in, let's say, air towards the ground, you have on the one side the object's mass times gravity, and on the other side you have the drag force. And since this drag force increases as the speed increases, so 1/2 C rho A V squared, and this one remains more or less constant, for some speed these two forces are balanced. When that happens, you have terminal speed. You can also include the buoyant force if you so desire, but for air that's a pretty negligible force. Essentially, when this condition is met, the sum of forces is 0, and so if the sum of forces is 0, that means that it's neither speeding up nor slowing down. So we can basically just set these two equal to each other and solve for the terminal speed, and what we get is m times g times 2, that's dividing both sides by 1/2, and then divided by C rho A. And so you could, if you prefer, switch it into terms of density of the object and density of the fluid, and that gets you the basically terminal speed for this object. If you have a spherical object, then you might further cancel the volume and the area and be left with a 4/3 of r factor. But it depends upon the geometry of your object, of course. So that's all for today's video. Hopefully you've learned something in it, and thanks for watching.